Okay, we're looking at problem 4a in the exercise section. We're doing related rates, which is really just implicit differentiation with respect to a third variable. Okay, so if you remember, we looked at this equation in the last section. X squared plus y squared equals 25. But just think of it, not as a circle, but as just some equation of x and y. Okay. Well, if x and y are two numbers that we were thinking about in this equation, okay, we could ask what happens or what relationship do these two variables have when they're changing with respect to some other quantity. Okay. So the idea with related rates in this section is that we can take an equation of two variables and figure out how their rates of change relate to each other with respect to some new variable. Okay. So what they're asking us to do is, in part A, is to find dy dt when dx dt is 8, x is 3, and y is 4. Okay. Now, a little bit of motivation. Why do we do this? Okay. Well, think of it this way. If x and y are two numbers going in this equation, but x and y themselves are changing, what can we say about the relationship between the rate of change of x and the rate of change of y? Okay. Well, that's what we're going to answer in this problem. It'll make a little bit more sense when we get to a real applied example. Okay. So basically, we see that we're looking for derivatives with respect to t. So that means we have to take the derivative with respect to t of both sides of the equation. Okay, now, when we're trying to compute related rates, that new variable, in this case t, we treat every other variable in the equation as a function of t. Okay, so let's look over here. I'm taking the derivative with respect to t of x squared. Well, that's not t squared, so the variable is different. The thing I'm squaring is different than the variable that I'm differentiating with respect to. So I actually use implicit differentiation here. Okay, I treat x as a function of t, okay, because that's the derivative I'm computing, the derivative with respect to t. Okay, so the derivative with respect to t of x squared is 2 times x to the power 1, or 2x, times the derivative of x with respect to t. Okay, when the variable you're differentiating with respect to and the variable you're raising to a power are different, you have to use the generalized power rule. Okay, if this had been d dx, it would have been the usual power rule. Okay. So it gives us this dx dt. Okay. Now the same thing goes for y, as it did in the past. We're taking the derivative of y squared with respect to a different variable, t, so we can only use the generalized power rule, which says when you take the derivative of something squared, you get 2 times that thing to the power 1 times the derivative of the thing you were squaring. So that's going to be dy dt. Okay. Now, over here, the derivative with respect to t of 25, well, a variable is a variable, a constant's a constant. The derivative of a constant is always 0. Okay. So, 25 is a number. It doesn't matter what kind of derivative we're taking, derivative of a constant is 0. Okay. So that's really an equation involving two different implicit derivatives and two variables. Okay. Now in this problem, they ask us to find dy dt when dx dt is 8, x is 3, and y is 4. Okay. So basically, the nice thing here is we don't have to really solve for anything yet. The easiest way to do this is take the thing you're looking for, we're going to leave it as it is, and substitute the other quantities for what we're given. Okay, they told us that we want to find dy dt when x is 3, y is 4, and dx dt is 8. So we just plug those numbers in. Okay, so the equation is going to become, so remember at this point I'm plugging these numbers in, 2 times x, which is 3, times dx dt, which they told us is 8, okay, plus 2 times y, so 2 times 4, dy dt. And that's the thing we're looking for. Okay, so we get this equation, which only has one unknown in it now that we've substituted particular values for the other. Okay, so what do we get here? Well, 2 times 3 times 8 is 48, okay, plus I've got 8 times dy dt equals 0. I want to solve for dy dt, so I subtract the 48 over, I get, let's see, it'll be 8 dy dt equals negative 48, and I can divide both sides by 8 to get dy dt equals negative 48 over 8, and that's negative 6. Okay, so that's what we were looking for. So the way to kind of interpret this is that if x is 3 and y is 4, but x is changing at a rate of 8, 8 units per unit of t, okay, y will be changing at a rate of -6. So y will be decreasing 6 units per unit of t. Okay. So when you want to ask a question about how two variables in the same equation are changing, clearly the rate of change of one influences the rate of change of the other. In this equation, just as an example, if x is getting bigger, y is going to have to be getting smaller in order for this equation to still be true, right? If x is getting bigger, we square that, it's getting larger here as well. In order to get 25 on the other side, y has to be decreasing. So we can see that the rates of change are related by that equation, and this is what we get in particular.